Hello, this is Arcades, and welcome to another how-to video here on Stormworks Build and Rescue. And yeah, this time we're going to be looking at control logics. So yeah, this should be interesting. In the case of this video, I'm looking at logic that ends up basically manipulating how logic is sent out and what values are sent out when, for the most part, and yeah, there might be one or two exceptions. We'll find out. Right. So, yeah, hope you enjoy what you watch. Hope you like what you see. If you do, remember to like, subscribe, leave a comment. Helps out the channel immensely. And yeah, let's get into this. Okay. So as you can see, I got the little demonstrator over there. I've already done two previous videos, one on arithmetic logic and the on-off logic, the Boolean logic, or the red. So the red and green logics I've already done. These particular logics here are pretty much what's left of the red and green logic. Now, just like the other ones, there are specific ones that are microcontroller only. I have them set up back there, as you can see. RTF, RTO, TOF, and TON. And those are all timer blocks. That's pretty much it. All the other ones are technically are available in the microcontroller and in the block form. Those are the only ones that are specific. Now, I will be going over one particular one again. I've done it in a previous video, so I'll go over it briefly again because I still think it should be included in this one as a control piece of logic. So yeah, yeah, so that's basically about the summary of what we're going to do, and I'll give a demonstration of each little one, so as best I can. So alright, let's get into this with the first one. Okay, so how we're going to do this, you see we got 3 rows here. We've got, and this is how I'm going to term them, this isn't necessarily official terms for classifying them, but we have our reactive ones. These create an output based on the individual numbers that are given, and they react to it. Then you have your actual control, you have your, I guess you'd say your manipulators. They somehow take the input logic and manipulate it out to a specific course value or something of that nature, and they do something with it. And then the final row are timers. They take the values input to create an output that fulfills your needs depending on your situation. So, not as many as the arithmetic, not as expensive as the Boolean, but uses both of those logics to use these. You can't use these without those other two and understanding those, so I would suggest go back there. So, first one we're going to get into. Right here, this is the greater than block. So, compares two numerical values, outputs an on signal if the first input is greater than the second, and the outputs an off signal if this first input is less than or equal to the second. So, come here, and you can see, again, the logic blocks have better descriptors of what's going on versus the microcontroller ones. Actually, the timer ones were actually pretty descriptive. I'll get into that later. But so yeah, you can see here, this is the value to compare. So this is going to be the value that you're taking in, and this is the value you want to compare it to. B is your, and then it outputs a signal, and it says outputs an on signal if A is greater than B, outputs an off signal if A is less than or equal to B. So pretty straightforward. It tells you, I love the descriptors. Now let's get this actually installed onto the demonstrator. Okay, so what we have here for our demonstrator, you see the yellow marker up there? That is following the contents, the tank content of this yellow tank. This tank, as you see, is full, should be fresh water. Yeah, it's full of fresh water and some gases, but that's a moot point. We're looking at the fresh water. Now, I have a comparative value of 200. So we're looking at A greater than B. As you can see, A is tracking 11, B is tracking 200, and 200 is the value is comparing. Now I have it hooked up currently, you can see the light there, but to show you as a proper use, I have an end effector on this door, and when it reaches that value, the door will shut, as well as light up that light. So, all we need to do to test it out is unlock it. As you can see, the value gets up there, and boom! The system shuts. Now this is a somewhat of an example of how you can use a volume control to close a door, like say a hatch, or when you're, flooding, or activate pumps, or such. This is where a good use for that scenario, so that you can, control different systems based on a numerical value. Okay, let's hit the next one. Okay, so now we're gonna look at the greater than's sibling. The less than block compares two numerical values, outputs an on signal if the first input is less than the second, and outputs an off signal if the first input is greater than or equal to the second. And you see your logic outputs and such and how they read. Go back here to again, value to A is the value to compare, so that's the value that you're actively watching. B is the value you compare to, the one you want to manage, that you want to use as your judgment to compare it with. And then you have your output, and it says outputs an on signal if A is less than B, outputs an off signal if A is greater than or equal to B. So just like greater than, but in reverse. All right, let me get this hooked in. Okay, so right here to our little demonstrator. As you can see, we're now monitoring the blue tank, which again is full of fresh water. We are waiting, put in a value to compare to 500. And it's all getting transferred from this tank to this tank. So again, like last time, when the value matches or becomes less than this, it will trigger the output to turn on the light and thus close the door as well. I'm not always using the door, but I figured this is probably a much better way to visualize how you could use it to control something. So, all right, and I open the valve. And there you go. It shuts it off. So you can see it got under 500, the light came on, and it shut the door. Okay, so the next block we have here is a threshold block. Threshold gate. Takes a value and compares it to a set threshold. A lower and upper bound to the threshold must be set. The output is set to on if the input value is less than or equal to the upper bound and greater than or equal to the lower bound. If it is outside this range, the output is set to off. The threshold bounds can be configured by selecting this component with the select tool. As you can see, it says has an input for a value to test and the on-off within threshold. Now what it's meaning is you can go into here, use your select tool, click on the block, and it will give you two values, a lower threshold and a higher threshold. There are things you can do to manipulate that, but we're not going to get really into that. I just want to show you the basics of how to work it, so we're going to use it as intended for right now. So we're going to set a threshold, for example, a threshold of 200 and a high threshold of 500. So as long as the values of what's inputted matches in between there, an on signal will be outputted from the gate. So you can take something, and if you don't want it to get too low, say for X reason, or before to trigger something to happen, or if it gets too high and you want that same thing to trigger, you can use this. Now, my favorite example of this is the actually control of lights using a clock. So give me one moment. Okay, so now I made a little adjustments, and just so you can see this, right now it's currently turned off, but I have the day durations and night duration set to 1, so a whole day cycle, and that will last 1 minute for the day and 1 minute for the night, and I've set the time to 5:34. I've set the thresholds for this to turn on at 8 a.m. or at 800 hours, and then turn off at 1600 hours. So it's monitoring the value of the clock, and I figured this was a good way you can use this to control your lights or different things based on the time of day. So with that, let's show this working. So I'm going to come in here and simply just turn off the override time. There, it's on at 8 o'clock. And boom, turned off at 1600. So yeah, that's threshold gate. So you can use it to control different systems, and based on values taken in, that it can turn things on based if a certain value hits in between, and then turn it back off once it gets out of that range. Now, what I was mentioning earlier, you could use a not block to invert it, or you can actually put the high value in the low slot and your low value in the high slot, and that would also invert it. Those are things you can do, but that's going to take experimentation to show you what it can do, and that is not what I'm trying to cover, but I figured I'd let you know it's something you can do, because if you were to take a not block and put it after this, you would actually have the light on at night, like for running lights on the truck, and off during the day. So, yeah. All right, let's get to the next one. Okay, so now, those were all of the triggers. These are ones that monitor stuff and then have a trigger based on what happens. Now these will manipulate outputs and adjust them or whatever based on inputs received from you or a system. So you can either directly control them, or you can have another system control them. They don't do anything specifically on their own per se. One exception out of this pack, but without an input from another source. I mean, technically all logics are like that, but you'll see what I mean, hopefully. So the first two we're going to cover, I'm going to do them back to back, and these should be familiar ones. Is first, we have the Numerical Junction. Acts as a junction for two number signals. The junction can be switched using an on-off signal. When the signal is on, the number is passed through to the first output, and a value of 0 is passed to the second. When the signal is off, the number is passed through the second output, with the first being set to 0. Okay, so what this means is we have 4 total logic inputs and outputs. 3 inputs and 1 output, or no, 2 inputs and 2 outputs, 2 number outputs. Now you have the switch signal, you have an on path, an off path, and then the value you want to send through them. If we come here and look at the actual logic, we have the switch signal, controls which of the 2 output paths the input value will be sent to. And you have this one is the value that passed through, the value that passed through the junction. And then you have your 2 outputs. You have the off path, receives the input value when the signal switch is set to off, and the on path receives the input value when the switch signal is set to on. So, what's happening here is that you have a value coming in. It goes into here. So say you have a 5. While it's in the off state, in other words, this is off, it will go through the off path. And this will go into one direction. This will be set to 0 while is off. So the value, while it's off, will go through the off path, and the other path will be set to 0. Now you hit this and you set it to on, the value that's coming in here will now go through the on path, because that's on, and you will go through here. So if you have the 5 value coming through, whatever is connected to this will now receive the value of 5. And everything that's connected here will receive the value of 0. So no value, value, while on, value, no value, off. And this is the value you're wanting to bring in. Okay, let me set up a quick demonstration. Alrighty, so here we go. So we have, as you can see, I have the junction box hooked up. It is reading the contents of this tank. So as you can see, we've got a tank content of 679.5, 679.5, and it's sending it up to the upper one. And you notice the other is 0. Now, as I said, there are 2 paths, an on path and an off path. Currently, it is off. So it is sending the value through the off path. Now, I want to switch it and send the data to another position. So I hit my trigger. See, it is now on through the switch input, and the on path has now lit up and is now sending the value out, while the other one is now sending out a 0. You can see I can keep switching back and forth, back and forth, back and forth. And if I go into this to release it, and you can see it just monitoring the value, and it will switch the values in between. And that's pretty much what it's for. Now, you might be asking, what would this be good for? Well, like I used it for changing out control inputs for going to like a VTOL. So for example, if you want your yaw, like if you're doing a VTOL and your yaw output is controlled through the rudders, but then you switch to helicopter mode, so to speak, you now want it to be controlled by your engines on your wings. Whether you're using pitch or rotating the engines, you want your yaw out there. And that's where you would then send your yaw data out to instead of to the rudders. Same thing with the roll and the pitch. You're going to want to send them to different places because the controls are different in those methods. So that is one example of how you could do it. This graphical thing I thought was pretty straightforward and helped you see what it was doing. Okay, do the next one. Now, for the junction sibling, and probably better known by everybody, is the numerical switchbox. Acts as a switchbox for 2 number signals. Which of the 2 inputs is sent to the output is determined by the on-off switch signal. When the switch signal is on, the first value is set to the output. When it is off, the second output is sent. Okay, so, and you can see we got our logic inputs, we got 3 inputs, 1 output, we have the switch signal, the first value on, second value off, and then the switched value for the output. So whichever one you decide is active, that's the one going out. Come here to the actual logic inputs, you will see we have the first value on, the output, the value to output when the switch signal is on, this being the switch signal. Second value off, the value to output when the switch signal is off. And finally, the output, the first value when the switch signal is on, and the second value when it is off. And then finally, we have the switch signal, controls which of the two input values will be sent to the output. So this controls which one of these is sent to here. So if this says a 5 and this says a 6, and this is turned on, this 5 will go through and you will see a 5. If it is off, the 6 that is in here will go through and you will get a 6 on the output. So yeah, let's get a little demonstration set up. Okay, got the demonstration all set up, and as you can see, the yellow marker there is displaying the value of the yellow tank, the blue one of the blue tank, showing their contents. And as you can see right now, by default, it is on the off status. So the switch value we're getting is the off value. If I go and hit the trigger, it switches, because you can see it's noting that it is on. And we are seeing the value from the on, thus it's lit up on the board. Bring it back, bring it forward. As you can see, as I switch, it reads the value from the one it's looking at. Even if we let this change, it'll let it change as appropriately for whichever one you need it to look at. Close. Now, the thing is the most popular use for a switch box that everybody knows so well is for a door. So in other words, you have the mechanical pivot, you have a data value in each of these for what position you want the door in. By switching, hitting that button and switching it, you switch the value input that goes to the door, and then the door rotates and it opens up. That is the most common use for the switch box that people have out there. And, you know, if you just want to change different, also if you just want to change which different things you look like, say you have, example like I have here, I have 2 different tanks, and you want to read through different tanks, you can switch through a bunch of these, you know, through different control schemes. So it has its uses. It's a very, very useful piece of logic. It's used, a lot of people use it in a lot of different ways, and when you stack it up with other systems, it gets really, really interesting. So, yeah. Let's get to the next one. Okay, so the next one I have technically covered in other places, especially in my Misfits logic video, the one that has, you know, logics that are primarily not in the microcontroller. And the reason why I featured it there, because it acts somewhat different from the microcontroller up and down counter. And I covered it there. I think I might have touched on it during my mathematic one, but I don't think so. So I'm going over here again because, as I said, it is a mixed color, and I figured, or you know, it uses both. It uses Boolean inputs to create a numerical output, so I figured this was a good case to go ahead and use it here, because that's the theme of this, is you have both red and green logic here. So I will be going over it briefly. I won't go into a huge thing for it, so we're going to go by this one quick. Okay, so we have the up-down counter. This component uses 2 on-off signals to move an internal value between -1 and 1. The up input moves the value towards 1, and the down input moves it towards -1. This component can be used for converting on-off button presses into a standard number value that can be used to control any mechanical components that accept a standard numerical input. So what you end up doing is you're using the up input and the down input to control the output that comes from here. Up moves the internal value towards 1. Moves the internal value towards -1. And this, the internal value between, the internally stored value between -1 and 1. So the interesting thing about this, we go down to the settings, is you notice there's a sensitivity. Now, it says between 1 and -1, but I think they may have expanded on it since they originally created it. Because I think it was originally supposed to be like a numerical logic box of a seat. Because I'm pretty sure it uses the same logic encoding as the seat axis does. And that's how it works, but then they expanded to give you a minimum, the maximum value, and a start value. I'm not sure. I haven't been around that long for the game, but it's a possibility on why it's different. However, so what you have here is your sensitivity bar, and depending on the sensitivity is how high it increases and how low it increases. The minimum value is where you want it to stop at on the low end as you're hitting down. Your max value is how high you want to get when you're hitting up, and your start value is where it wants to sit by default. Pretty simple, straightforward. Let's get a quick demonstration up. Okay, so got it set up here on the board real quick. I have here on the handle, I have set my hotkeys for 1 and 2 to up and down. 1 is up, 2 is down, and yeah. So quick show off. So we're gonna go up. As you can see, I've got it toggled on, and the number is going up. It stopped at 1. I hit 2, it goes down. Now if I put both together, as you can see, it stops dead. So I take that, it goes down, and it runs towards -1. So yeah, pretty straightforward. Makes the number go up and down. You can use in places where you need to use, you know, a number adjustment. Like I said, I think it originally was designed to be used as a kind of a replacement, like, axis for the seat, and it works kind of in the same way, but it just uses a button input instead of your A and D, WASD, or the arrows. So yeah, pretty straightforward. It goes up and down. It's a number counter. You can change the settings and such. I did, for this example, lower the sensitivity so it was easier to track the number. But yeah, other than that, yeah. All right, let's get to the next one. Okay, now what we have here is the memory register. A memory register that can store a number value. The number input will be stored when an on signal is received. A secondary on-off signal can be used to clear the stored value, resetting it to the configured values set in the select tool. We have 3 inputs, 1 output. You have the value to store, you have a set, you have a clear, and then you have the stored value. Now what this is used for is basically remembering a number. So if you input a number in a keypad, so to speak, you can then basically say, click another button, and it will remember that number. And then you can pick another, do another one, and say, clear it. So you have one button to say, hey, clear that number register, put it back to the default value, and the other one, when you go to put it, you find a value you want, you can set it. And then you have the number input. And then the output is the, well, number output. So let's take a look at the logic inputs. I feel like this is so backwards, but this is the way it came in, I swear. Anyways, okay. So we have the value to store, and then we have the stored value. Then we have clear, resets the stored value to 0, and then set stores the input value when receiving an on signal. So here's the thing. I think I haven't used it very often, okay, for most of my stuff, so I will say I haven't used it very often, but I believe while this value is on, it will take whatever current value is coming in. It's not until you hit it and then release it, so where it's on and then back off, that it keeps that value. This is kind of important in some premises. And then when you hit this on, it takes that value and clears it. If you hold this on, I believe it won't store even if you press this real quick. It stores the value, but it will keep storing whatever the currently active number coming in is while you're holding this on until you let it go, and then it takes whatever value is currently at that time. And then whatever this value is, it outputs it here. Okay, so we got our little demonstration up there. As you can see, it's already lit up. I have it connected to the blue tank, again, as usual, so it's reading that value. As you can see, it has nothing stored right now, so it's reading an output of 0. Now, I have the space bar set for clearing, and 1 is for setting. And if I hit spacebar, it clears the value. 1, it remembers. And as you can see, if I come over here now and we hit the valve, it changed the value, but it remembered what was up here. Now if I come up here and I just hit 1 to set the value, it remembers it. Now, like as I said a moment ago, if you leave it on and you hit this, it will change it actively as it changes. So I come back here, hit it again. As you can see, it can change and the other will not. Now, we hold this and we hit the reset at the same time. The reset takes active regardless of whether or not the one is set. So, yeah, I'd say it's straightforward, but it's not. But it is a way to remember numbers, and you have a way of erasing them as needed, as necessary. And the one inside the microcontroller works pretty much the same way. Uses for this. The first and foremost is remembering waypoints when you want to set in multiples. There was one ship, a really old design, had probably still like the best autopilot system I've ever seen in a ship. You could set in 3 different waypoint values, and it would go to those 3 points in order. So you could plan out ahead an entire trip, and the ship did it amazingly. So, you know, that's one example of how you can use this to save, like, waypoints. Obviously, in the case of this, it would be saving an X value, a Y value, and their own separate blocks, times 3, so that'd be 6 memory registers. That's a big pack. But, nonetheless, it did work. And this was also before Lua and the microcontroller, so, yeah. That ship had a lot of red and green lines, so to speak. Anyways, but that's one example, and various other things. Or you want to save a heading, or just, you know, various things. If you need to save data for a moment. Or another favorite one is altitude holds. You can save a particular altitude, or, you know, hit the button, save your current altitude, and the machine, and then it will hold that for the, you know, the alt hold to come back to. Okay, to the next one. Okay, I was debating whether to even include this, because technically this one could use its own video just on its own. And to be honest, I'm not an expert at it. I have the vague idea of how to use it, and I use it for the engines. What this part is, it's the PID controller. Now, if you've seen, I have a video about using PIDs to control your engines. It's a basic use of the PID, not very in-depth. I'm not going to be able to go in-depth on this one at all. That is not my specialty. I can give you the basics of how to fill its things, and a base thing of where to use it, but as far as a detailed description on how to use it, that's not me. Sorry. There's a lot of people who are much better with PIDs than I am, who can answer any questions better, but I will at least tell you how you set it up and use it and give you some basic use so that you can have a foot in the door so that you can talk to somebody for any other questions. This one I'm going to say, look elsewhere. Ask me questions, and I will answer best I can, but if you get really technical about what to do here and there, I'm going to tell you just ask somebody else. Hey, because this one just, it's not horrible, but at the same time, it's easy to learn, hard to master. Very much. Okay, with that out of the way, what do we have here? The PID controller, a controlled loop feedback mechanism that measures and corrects the error in a system over time. It takes the current measured output of a system or sensor and a desired target measurement. It outputs a value that can be used as an input to the system to gradually correct its error. For example, the controller could input into an engine's throttle to maintain a desired speed or altitude. The control terms, proportional, integral, and derivative, can be set by selecting the components with the select tool. The control terms must be carefully tuned for optimal output. That is an understatement. Okay, so we have for our logic inputs and outputs, we have an on-off active, we have a numerical for a set point, a number for process variable, and then you have a control output. I'm sitting here trying to think how I should demonstrate this. Because, I mean, technically I've already kind of demonstrated with my ECU video, which I highly recommend you go check out, because I go a little bit better in depth than what I'm going to do here. I don't think I can give a proper setup within what I want to do here. So I am... Oh, no. There is one thing I can do. Yeah, there's one thing I can do. So. Okay, so we look at the inputs. We have the set point, which is the desired value to correct the process variable to. We have the process variable, the current measured value of the system. And then we have the control output, the output computed by the controller. The output that is computed by the controller. And then you have the active sets whether or not the controller is active. When inactive, the stored values are reset. Meaning when you turn it off, it just goes to 0. That's all it does. So in other words, it shuts itself off. If we go to select this, you see there are 4 values here. You have a proportional gain, integral gain, and derivative gain. All these values work together to create a calculated output. The max value, I believe, refers to the output from here. Its value will be within plus and minus of this value. So if you put in 1, the max value, it will max out between 1 and -1. So if you put in 2, it would be 2 and -2. That's what everything I've seen points that it does. So yeah, it's a very, and this is a very useful value. It's kind of like the clamp built into it, and it's very useful for keeping this from going out of control, especially if you're putting in an engine. So you're actually maximizing the amount of value for the engine that it's outputting by limiting it to 1, because that means max 1. However, that also gives you the range of -1, and that can be a bit of an issue. Now, I am going to go to the wiki, and I'm going to read off what each of these mean. And that's about all I can really do. I have a small demonstration I can pick up and show you for something, and hopefully it'll work. Just give me one moment. Okay, here we go. Proportional. The proportional term produces an output value that is proportional to the current error value. The proportional response can be adjusted by multiplying the error by a constant value called the proportional gain constant. A high proportional gain results in large changes in the output for a given change in the error. If the proportional gain is too high, the system can become unstable. In contrast, a small gain results in a small output response to a large input error and a less responsive or less sensitive controller. If the proportional gain is too low, the control action may be too small when responding to system disturbances. Tuning theory and industrial practice indicate that proportional terms should contribute to the bulk of the output change. So they're basically saying your proportional is probably your heavy lifter, and this will do most of the work. Integral term. The contribution from the integral term is proportional to both the magnitude of the error and the duration of the error. The integral in a PID controller is the sum of the instantaneous error over time and gives the accumulated offset that should have been corrected previously. The accumulated error is then multiplied by the integral gain and added to the controller output. The integral term accelerates the movement of the process towards the set point and eliminates the residual steady-state error that occurs with a pure proportional controller. However, since the integral term responds to accumulated errors from the past, it can cause the present value to overshoot the set point. Yeah, to overshoot the set point. So basically what it's doing is it's trying to say, hey, yeah, you're a little bit farther, so let's try to go a little bit farther, but the problem is sometimes trying to go farther will cause it to go too far, and then it brings it back to things. So it slowly levels it out by going back and forth over the line of where you want it at. Derivative of the process error is calculated by determining the slope of the error over time and multiplying this rate of change by the derivative gain. The magnitude of the contribution of the derivative term to the overall control action is determined by the derivative gain. Derivative action predicts system behavior and thus improves settling time and the ability of the system. An ideal derivative is not casual, so that implementations of PID controllers include an additional low-pass filtering for the derivative term to limit the high-frequency gains and noise. Derivative action is seldom used in practice, though. By 1S, only 25% of deployed controllers, because its variable impact on the system stability in real-world applications. So basically, as I'm understanding what I read there, it basically dampens how hard it will bounce. It tries to settle it in by reducing how hard it will shake back and forth across the line of what you're aiming for. But however, it's acceptable to other systems, so it can kind of mess it up. So yeah. That is the terms from the wiki. So hopefully, if you want to go look there for more information on how to use the PID, I would suggest going there. So yeah, let's actually get into the demonstrator, see if I can put up something that isn't just an engine. Okay, that one took a while to set up, but yeah, I went down to the electric motor one that I had in my ECU video, so I figured it'd be a more interesting setup. Now, I put in a value for what it is. My target value is 8 RPS that I want this to run at. It is reading the RPS off the torque meter right there. As you can see, no RPS, no RPS. Set point is set to 8, process variables 0, and the control output is 0. That right there is the control output. What this is sending out. So that's reading the RPS of the torque meter, and so on and so forth. So I come in here, I turn it on. As you can see, it's slowly bringing itself as close as it can get to 8 RPS, which in this case, it's going to stop around 6 RPS on the thing. And you can see it's managing the throttle to bring that 6 RPS. Now, this obviously will change depending on the load I would put on it, because I just have this on here. It's just going for the straight RPS value. You can see, doop, and doop. So, yeah. I'm not going to say it's straightforward. It's not. It's really not. It can be simple and easy to use for minimal things, but you want to get to the really nitty-gritty, it begins to show its teeth. So, it can be easy, but depending on what you want to do, it can be very challenging. Now, another thing that people use this for is not only engine control, but altitude holds. I've used it for, managing the rotor, the rotor torque and such on another controller. So it has different purposes and values. So yeah. All right, let's get to the next set. I'm done with that monster. So we're going to be looking at the RTF timer. This one has 3 inputs. It is the timer enable, the numerical duration, and then an on-off for the reset, and it outputs an on-off signal. A variable input timer outputs an on signal when the timer is less than its duration. the timer will not reset until it is signaled. Now, one thing they're not exactly clear about, but the thing is this one, while the duration is going down, it will present a on signal. And then once it's complete, it will stop presenting an on-off signal, an on signal, until you hit reset. So even if you have the timer held on enable, it will count down its duration and then it will stop. And it will not restart until you hit the reset. Even if you have the timer enabled, still on. Yes, this sounds a lot weirder than it should. But it's just basically saying it only presents an on value while the duration is happening, is what it's going to do. And it will not do it again until you hit a reset for it. Okay, so we got a bit of a demonstrator here set up. So I've got 5 seconds on the clock for the duration, as you can see. Went ahead and added those. We've got I have one set as reset, spacebar as activate the trigger. So I'm going to hit the trigger. You can see it turns on. This will sit for 5 seconds on and then it will turn off. Now, while this is set as on, I can hit the reset button. See, reset, and it will start counting down for the 5 seconds. However, it starts from the moment I let go, because it's still seeing the on signal, so it's constantly getting reset, and it will stay on while both of these are on. However, once I let go, then there's a 5 second duration that it will count through and eventually shut off. And that is your RTF timer. Off to the next one. Okay, so the next one is our RTO. Variable input timer outputs an on signal when the timer reaches its duration. The timer will not reset until it is signaled. So unlike the other one, which did it during the duration counting down, this one will not turn on until the duration is over with, and then will not turn off until you reset it. So let's take a look at this. Oh yeah, we have also when you go to select these, you can choose the units that the duration lists as. So you have the seconds and ticks. Now, ticks there's 60 ticks in a second. So that means you're looking for an interval smaller than a second when you're using ticks. Seconds is, well, seconds on the clock. But like I said, there's 60 ticks in a second. The same goes for the RTF. I know I didn't cover that with it, but it's the same here. You have your timer enable input, you have your duration input, and you have the reset input. And then finally the timing complete output. I really wish they gave more information on these. The microcontroller ones are so Spartan versus all the original stuff. Okay, give me a moment. Okay, so I went ahead, we're gonna look at all these as a constant 5 seconds, because I think that's pretty universal. It's just enough to see a difference. Now, again, the space bar is for activate, the one is to reset, and we have 5 seconds on the clock. So I hit the button, as you can see it's active, so the timer is going to be going down, and then after 5 seconds, it turns on. Now here's the thing, I go to deactivate, it turns it off. Reactivate, it turns back on, because it's considered it is cleared through its duration. And it will stay like this until you hit the reset, at which point it will stay off until it manages to go through its duration while the timer is active. So, and as you can see, I reset it. 1, 2, 3, 4. Now if I let it stop here for a second, wait a little bit, turn it on, and then blink. So as you go along, it counts down while it's active. You turn it off, it stops counting down. Turn it back on, it continues where it was before until it finally hits 0. So keep that in mind when you go to use this. If you leave it on, just hitting it will just automatically just reset it. And as long as you keep hitting it, it won't come on because it never gets the chance to fully go through its duration until it does. So, okay. Yeah. So, let's get the next one. Okay, so this one is the TOF timer. Variable input timer outputs an on signal when the timer is less than its duration. The timer will reset when it's off. Now, the main difference between the two, there's the 4 timers is 2 of them are reset manually and the other 2 reset automatically. So the first 2 you have to reset manually through a different method. These 2 will automatically reset. Once their duration ends, they will automatically reset. But however, it says it will reset when it's off. So that means when you go to use the timer enable, you have to turn the signal off to reset it. So this is just like the RTF, except in this case, you have to reset it by turning it off. By turning off the timer enable input. Alright, let's go check this out. Oh, hold on. By the way, seconds and all that, and as you can see, it only has the 2 inputs, enable and duration, and then timing. Okay. Okay, so we've got the next one listed right here. And as you can see, still 5 seconds, and the same buttons do the same thing, except one does not reset, so all we have is the activate. And as you can see, it comes on, it's less than its duration, so finally it just goes out. And since there's no reset now, just turn it off, turn it back on, and you can see. But it won't last longer than its duration, no matter how many times I reset it on and off. Okay. Yeah, that's pretty straightforward. So let's get into the next one. Okay, time for the last one. Variable input timer outputs an on signal. When the timer reaches its duration, the timer will reset off. This is the TON timer, the ton timer, whatever you want to call it. So basically, it goes through duration and then it outputs a signal. And as long as you have the timer enabled, active, it will output an on signal. Once you turn off that, it will reset and you have to go through the timer all over again. So, and like the other ones, you have I really don't. I wish I could just clear this with a single button push. Anyway, so we have it here. You have your timer enabled. You have your duration. Those are your 2 inputs, and of course your timing complete output. Let's get to a demonstration. Okay, so now we have the last one. The last logic I'm going to cover for this video, and this is the TON timer. And as I said, it will output a on signal after the duration has been completed. With a simple push, it begins what it's supposed to, till finally flips on. And then it will stay on until you turn it off. And should you reactivate, you have to wait the 5 seconds one more time. Boom. Just like that. Okay, so yes. Whew. Okay, so that was the last bit of logic I was going to cover for this video. Now, quick review, we have back here from the bottom there to the top, we have the greater than, less than, and the threshold gate. They use numerical inputs to test the value against and then put on a on-off signal based on the results of those inputs being compared. Then on the next row, you have your manipulators of data, taking numerical inputs or on-off inputs and changing the output through a numerical means or through a Boolean means of on and off. You have your junction on the first one, which allows you to switch the direction of your numerical output using an on-off signal. You have the switchbox, which you can choose which source to pull a numerical value from to send out to somewhere through an on-off signal. You have the up-down counter, which uses on-off signals to change an internal value, an internal numerical value, and send it somewhere. You then have the memory register, which can take a value, which you can set it to remember at any given point, and then recall it out to somewhere, and then you can clear it and set in a new one with the on-off inputs. Then you have the PID, which, depending on the values of your set value and the value of your process variable, it will change its output to control a system as you want it to. You can activate it through the on-off system to make sure whether it works or not. And finally, on the last row, we have the timers. We have the RTF, the RTO, the TOF, and the TON. The first two have a manual reset. The last automatically reset after the timer enables are released or turned off, so to speak. And the first and the third one will put an on signal while the duration is going down and shut off afterwards. And the other two will put on a on value after the timer duration has gone through, and then they will put an on signal. Whew. Okay, that was a quick overview of all that we looked at. So, yeah, I hope this was helpful. If you have any questions, put it down in the comments. Try to answer them best I can. I am not perfect. I don't know everything, but hopefully this gives you enough that you can get in the door and work your way through the systems. So, hope you had a good time. Hope you enjoyed watching. If you did, you know the deal, you know the spiel. This is Arcades, signing out. Have yourself a good day.